Hi everyone, we're going to kick off with week 9 course notes and we start algebra. Woohoo! So, the concept of algebra is just that, okay, we're going to use some symbols to replace numbers. We may not know what the number is, and until we find out, we're just going to call it x. And that x, that n, that y, that alpha, whatever you want, it's still a number, we just don't know what it is yet. So that's what algebra is, replacement of numbers with what we refer to as pronumerals, as in basically symbols, letters mostly, or we call them variables because the meaning of x can be 6, can be 4, can be minus 3.82, we're not sure. So anyway, whenever we refer to variables, that's the letters, that's the pronumerals, it's the symbols. And mostly in algebra, yeah, it's letters. We're just going to mostly use, A, B, C, X, Y, Z. So, we need to look at the laws of arithmetic that happen with algebra, and it's going to be exactly the same as the laws of arithmetic that happen with numbers, because algebra still is numbers. Anytime we're confused by an algebraic statement, we can think, well, that's just a number. I can pretend x is 5, just to see how it makes sense. We'll get into that more. Firstly, the basics. Any letter or symbol may represent a number, but like I said, we're going to use mostly letters. Okay, and we call them variables, mention that. 2n means 2 times n. The same way we've had this before. When you've got a number, there were some exercises at one stage, I think, where you had a number up against a bracket. And the 2 plus 3 we know to do first. What happens in here? Well, if there's nothing written there, it's a times. A number up against a bracket is a times, in the same way that 2n, a number up against a variable, a letter, an algebraic term, that is still a times. That's 2 times n. And n means 1 times n. I mean, you can say 1n is 1 times n, absolutely. But 1 times n is still n. We don't bother writing the 1. But there can be times when you might have a question that says, what's 1n plus 2n? Or, sorry, I should have said, what's n plus 2n? And some people like to say, well, I just want to remind myself, that's 1n. I'm talking about 1n plus 2n is 3n. Okay, so you can put the 1 back there if you want, but hopefully it's going to be okay to say, what's n plus 2n? And in algebra, that's like saying, n might be a nectarine. What's nectarine plus 2 nectarines? 1 nectarine plus 2 nectarines? Well, it's 3 nectarines. Okay, that's a bit of algebra. By convention, we place the number before the variable. I'm not wrong to write n3, but we prefer to write 3n. Okay, it's by convention. We like to write the number and then the letter, or the symbol. By convention, we also put the letters in order, but it's not always. You'll get questions that talk about BA, an algebraic term BA. We just need to know that, look, BA and AB, they're the same thing. B times A and A times B. Again, B and A are just numbers. If you want to analyse the laws of arithmetic here, you say, well, maybe B's are 3 and A's are 2. If that's the case, we'll just say 3 times 2 is the same as 2 times 3, and so of course it is. That's one of the laws of multiplication, that they can move around. The commutative law of multiplication was that the order didn't matter if they're all timeses. Well, it's the same with algebra. I can replace them with any numbers or letters. AB equals BA. Same answer. Okay, so adding and subtracting algebraic terms. We have to talk about like terms. The example I just did then was I said like n plus 2n equals 3n. And I was saying that's a nectarine plus 2 nectarines is 3 nectarines. Hopefully that makes common sense. Same with 4x, 7x minus 3x. They're all like terms. But 3x squared and 7x are not like terms. Like if I just said, what is x plus x squared? Well, I can see they've got something in common because there's x's involved. But an x is a different thing to an x squared. An a is a different thing to an ab. An ab is a different thing to a bc. These are just not the same things. But if I've got 2x squareds plus 3x squares, I'm comfortable with that because x squared is a thing. It doesn't matter whether you know what it is or not, but it's a thing. What's 2 of these things plus 3 of these things? 5 of these things. And the thing doesn't change. I don't call it something new, some fancy new name. It's like I've got a thing down here that says, and I said, as odd as this example may seem, if someone asks me what's 2x plus 3x, I say, well, you've got 2 x's and 3 x's, you've got 5 x's. Okay, that's like saying what's 2 chairs plus 3 chairs, it's 5 chairs. Now, x squared, I said, was also a thing. Maybe that x squared is a, well, here I said a stapler. Again, I know it sounds stupid. I'm just saying x and x squared, they're different things. Okay? But what's 2 staplers plus 3 staplers? It's 5 staplers. This thing doesn't change. It's just 2 of these things plus 3 of these things is 5 of the things. Then someone says, what's 3x plus 6x squared? And I go, well, there's nothing I can do with that. What's 3 chairs plus 6 staplers? I can't add these 2 things. Chairs and staplers don't add. Okay, so if someone asks us to simplify 2x plus 3x, I'll write 5x. Simplify 4x squared plus 5x squared is 9x squared. But simplify 3x plus 6x squared, I'd say, no, it's 3x plus 6x squared. Nothing wrong with it, but I can't simplify it. Unless they tell me what x stands for, and I can chuck it in there, I can't simplify it. So, and here we say that x, y, and yx are the same. I've used the same example, predictable. So let's look at some examples. Here it's saying it can be useful to rearrange terms in an expression before simplifying an expression. And I've given the example just with numbers, 4 minus 20 plus 30 minus 3. Now there's no need, I can just go left or right here and just add and subtract all of these. That's what order operations tells us. But I just want to note that you can move these things around if you want, but everything owns the sign to its left. And even though there's nothing there, we know nothing being positive. I've got 4 things there. Now the order in which I write them makes no difference to the final outcome. As long as if I'm going to move them around, I've got to move the sign with it. So I might leave the minus, well, what did I do here? I might leave the 4 there and move the minus 3 to it. I might leave the minus 20 there, put the plus 30 there. Really all I've done here is move that into there. But everything's still the same. I've still got a plus 4, a minus 3, a plus 30, a minus 20. That's all good. A 4 minus 3, well, we don't need to go ahead with it, but I will just, I don't know, ACD. We've got a 1 minus a 20 plus a 30 is the same as plus a 10. So I've got 11. Okay, well that's just numbers. All I'm saying is you can do the same with algebra. Let's remove that. If someone says, what have we got down here? 4b cubed minus 7a plus 2b cubed minus 2a. Truth is I don't actually physically move them. I do in my head. If someone asks me to simplify that, in my head I'm thinking, well, you go with you because you're talking about b cubes, and you go with you because you're talking about a's. But I can look at it and say, well, it's 4b cubed plus 2b cubed. Well, I've got 6 b cubes. Whatever the b cubes are, I've got 4 of them plus 2 of them. With the a's, whatever the a's are, I've got minus 7 of them, minus 2 of them. So all up, it's like someone took 7 a's away from you and then took 2 a's away from you. What's happened? You've had 9 a's taken away from you. Go back to, well, I don't know what week it was, but minus 7 minus 2. Remember, this wasn't a case where 2 minuses make a plus. 2 minuses make a plus when you times things, divide things. All the signs are next to each other, none of which is this case. Minus 7 minus 2, the analogy I used was I walked 7 steps back, then I walked 2 steps back. What have I done in total? Minus 9. It's still the same thing, but it's just minus 7a minus 2a is minus 9a. So we don't mean physically that you have to rewrite them in a different spot, but you do need to group things. And again, everything owns the sign to its left. I group those two, which are both pluses. I group the minus 7a and the minus 2a to make the minus 9a. So I collected like terms. The terms were like. They were describing the same thing. Another one here, trying to trap us with a 7xy and a plus yx. Well, I know yx is an xy. So I've got a 7xy plus an xy. That's why I'm going out with 8xy. I've got a minus 12 and a minus 5. There's my minus 17. Everything owned assigned to its left. And I can just collect the similar things. Now, multiplying and dividing in algebraic terms. Well, we've got index laws that are going to happen. Just need to check again. I think it's last week. X times an x squared is x cubed. So x times x squared is x cubed. 2 ways to think of that, even though it's revision. I can think of x squared as an x times x, so really it's an x times x times x. Or I could have used the index laws and say an x is the same as an x to the 1. Anything to the power of 1 is still itself. So that's me showing that I could have said, oh, look, all I'm doing is when you multiply the same base of x, you add the powers. Again, that was our indices topic. Whichever way we look at it, we've got to remember that we've got our index laws, and that's going to be useful here. I'm going to delete again. Simplify the following. Okay. 7y times 4x. Oops. 7y times 4x. Again, I've written some middle steps, which is not really what I do. I don't really write it all with times in between them. But that's just saying that, look, really there's a times between the 7 and the y. There's a times between the 4 and the x. I can move these around if I want. And then it shows that I can move the 4 with the 7 and the x with the y. What would I really do? I would look at the numbers. 7 4s is 28. And I'd say y times x, well, I'm just going to put in alphabetical order. 28yx wouldn't be wrong. Either would xy 28, but 28xy. That's all I've got to do. It's not, I mean, you can still say it's like terms. I put the numbers together, and then I put the letters together. But really, like terms is a term more for addition and subtraction when I've got to have like terms. Here I don't. I can multiply an x and a y. They don't have to be like terms. Like if someone asked me what's 7y plus 4x, I would say no change. I can't just like add the numbers or something like that. 7 chairs plus 4 tables is 7 chairs and 4 tables. Then my analogy breaks down. Oh, so you can say 7 chairs times 4 tables, and I go, oh. don't call me on this. There is an analogy that I've used before. I don't know whether I didn't mean to go here with this. But I'm going to try it. What's 2 meters plus 3 meters? Well, a 2 meter length plus a 3 meter length is a 5 meter length. I can add lengths. What's 2 meters times 3 meters? Well, that would be a 2 meter by 3 meter area. 2 by 3, that'd be 6. And I'll report it as 6 meters squared because really it's made up of 6 individual 1 by 1 meter squared. Well, that's the same as algebra. 2m times 3m is 6m squared. The 2 by 3 is a 6, and the m times m can combine to become an m squared. What about unlike terms? Well, if I said what's 2 meters by 4 meters squared, might be an odd looking thing, but and I didn't mean to go here. Please take this as a tangent that's only useful if it's useful. Oh, I shouldn't make videos on Saturdays. Here's me with a 4 meter squared mat. It's a 2 meter by 2 meter maybe. So there's a 4 meter squared mat. If I multiply it by 2 meters, it's like I'm forming a cube out of it. So was I allowed to multiply 2m by 4m squared? You bet. 2 by 4 is 8. M by m squared is m cubed. I got an 8 meter cubed item here. There's 8 cubes in this thing. Worst picture ever. I didn't plan that. So what was the point, David? Like terms, there have to be like terms in order to add, but I can multiply unlike terms. I just combine them. Okay, so very different. This one down here, what have we got? Very unlike terms. Are you going to draw for me? Oh, thank you. Y times 3y squared times 4y cubed. Well, down here I've rewritten everything, but I'm just going to say, look, it's like there's a 1 there, if you want. I've got, the only numbers I've got 1 by 3 is still 3, 3 by 4. It's a 12. Now y, I can think of y as a y to the 1 if I want. I normally don't, but if you know 1 plus 2 is 3 plus 3 is 6, I can say that way it's y to the 6. But as soon as I see a y, okay, there's a y there, y squared means y by y cubed means y, I can see I've got 6 y's there. So yeah, multiplication is much nicer. You can get all these things and just bring them together. Even if they're all totally unlike. Like what's AB times BC times CD? They're all unlike, but I could initially go, well, you're AB, BC, CD. That's still right, but let's tidy it up a bit. I've got an A, B times B is a B squared, C times C is a C squared, and there's a D there. Okay, I've tidied it up. Alright, another. Then I put in a division. I've got a 15y squared on y cubed. Now there's an option 1 and an option 2. I'm an option 2 person, but I'm going to do option 1 first anyway. Option 1 says, oh, didn't write the 5. Option 1 says it's like I consider it to be two separate fractions. But what I'm doing is just looking at the 15 on 5 and saying 15 divided by 5 is a 3, and y squared divided by y cubed is like this. Y squared divided by y cubed is a subtraction of the indices. That's what we did last week. 2 minus 3, well, that's minus 1. So y squared divided by y cubed is y to the minus 1. That is the perfect answer. The option 2 that personally I prefer is saying, well, I've got 5's in common here. I've got 1 5 there and 3 5's there. Here, I admit I'm picturing it like what I've drawn here. I picture y squared as a y and a y cubed as a y. So if I'm going to get rid of y squared, that's me saying that's 2 y's I'm getting rid of. So what am I left with? That was 3 y's. I'm left with a y. Okay? Look at it like here. I had 2 y's on the top, 3 y's on the bottom. If I cancel some y's, I've got a y left on the bottom, which is 3 on y. Now here's a pretty important point, that those two answers are exactly the same. If it was multiple choice, either answer could be there. You would need to know that, hang on, that's the same as mine. And what I've got here is proof that it is the same. 3 times a y to the minus 1. Now the power only affects this y here. It's not like it's all bracketed saying it's everything to the minus 1. No, the power only affects what it's to the top right of, which is the y. So that 3 is just the number 3 on 1. And what did y to the minus 1 mean? Well, the minus meant 1 over, and y to the 1 was just y. And what do I do with multiplication? I times across the top to get a 3, times across the bottom to get a y. Yeah, it's the same thing. So that and that, it's important to know are the same answer. Okay, now substitution, well, it's the nicest part of this, which is it's not even algebra really. It's stopping the algebra. It's saying instead of having letters, I'm going to give you the numbers they're meant to represent. So that sounds pretty easy. It's not bad. The only thing, and I've put it in bold, this is the main thing that causes trouble. When substituting a negative number, place brackets around it. And I'll go straight to the first question. And there's 2 ways that a number can be squared. Now, let me just ask you these 2 questions. One question I'm going to ask you, I'll use 5. Minus 5. I'm going to ask, what is minus 5 in brackets squared? And what is minus 5 squared? Now, we have done it before, but I just want to check. Minus 5 in brackets squared means get everything in these brackets and times it by itself. Alright, everything in the brackets is a minus 5 times minus 5. Clearly it becomes positive. Now this one, well, the square is only applying to the 5. There's no brackets saying, hey, include the negative. This question's the same as like if I wrote minus 1 times 5 squared. An order of operations says you've got to do that squared first, not the times. So it becomes a minus 1 times 25, which is a minus 25. So if only the 5 gets squared, it's like the minus sits there, and we get minus 25. So there's 2 opposite answers to a very similar looking question. That's what happens here. And the point I'm making is, if someone says x equals minus 3, find x squared, they're saying whatever x is, minus 3, put it here and square all of x. X squared means x times x. So it means, what's x? Well, x is minus 3. Well, it means get the x and times it by itself. In other words, long story short, whenever you sub a negative in to an algebraic expression, give it brackets, because it means the whole number. If x is minus 3, it doesn't mean x is 3, and later we'll look at that minus. No, and x is entire minus 3, so times it by itself, and we get the outcome of what we looked at before in brackets. So if you're subbing a negative number in with brackets, I really don't see too many things that are going to go wrong. It's going to be our basics at fault if we're getting mistakes here. Let's look at the next one. X equals minus 3 again, but this time y equals 4. And it says find root y minus x. So, okay, well, root y, that just becomes root 4. And it says minus, and then it says x. And I'm going to replace that x with a minus 3. Now, agreed, you could say those brackets don't really matter. But maybe it clarifies to me, oh, I've got a minus minus. Okay? Firstly, the root 4 I've got to do first. Root 4 is 2. And I can write it with or without the brackets, but as long as I spot that those two minuses make a plus, that is 2 plus 3, that is 5. Okay, so yeah, I just find it, well, I mean, sometimes you might write 2 minus minus 3 and go, oh, is that 1 minus or 2 minuses? Well, I think the bracket helps that, okay? Even if you're messy, like, I'm trying not to be messy. I'll try harder. Okay, the next one, we've got a few things going on. It says, find x, y squared minus x squared z. My 2's and z's look similar. I shouldn't ever use z's. Now, I've done the work in there, but what, x is minus 3, so I'm going to put a minus 3 in brackets here. I might write my times to remind me that I know that when there's no sign between them, it's a times. Then it's y squared. I'm not going to bother putting the 4 in brackets. It's only the negatives I care to put in brackets. Then it says minus, now x squared, so I'm going to put it in brackets again, times a z, which is a 5. Okay, well, we've got to do the brackets first, but there's nothing inside these brackets to do. It's just a number. So the next thing is the ofs, or the order ofs, the indices. So I've got a minus 3 times 16. I'm leaving the brackets out now because I'm clear it's a minus. It's not getting squared. It's not essential anymore. Then I've got, well, I don't have a minus minus because that minus 3 is getting squared. That's got priority. And I know minus 3 times itself becomes that. So there's only a single minus there. That minus just disappeared. The minus 3 times 16 has to be a minus 48 because a minus times a plus and minus. And minus, well, 9 5s is 45. Now I've got to be careful. They're all backwards. I went 48 steps back and then 45 steps back. And I admit this line is not essential, but just to make it easier, I'm splitting this up. And we've got calculators. I keep doing this. But I've just split up my minus 48 into a minus 3 and minus 45, just because 45 and 45 combine so well. But really, you can ignore that. We are a calculator course, but not bad to know how to do things without a calculator, how to make life a bit easier for yourself. But yep, minus 93. Okay. Algebraic fractions. Whoa, moans. Fractions are back. And fractions, algebraic fractions, we're back to non-calculator stuff because we can't put algebraic fractions in the calculator. I mean, the calculator can still help us at times, but we need to know, we need to revise our manual work with fractions. How to add them and subtract them, which means you've got to have a common denominator, and how to multiply and divide them, which means you don't need a common denominator. They're the nicer ones. But let's start with the nastier ones. First question it's got, actually I'm going to put a different question in first. Algebraic fractions. What is x on 7 plus 4x on 7? Well, if they've got the same denominator, fantastic. I don't need to change anything. All I've got to do is add the tops. X on 7 plus 4x on 7, well, x plus 4x is 5x's. So really that was the question. That was just like, what's a seventh plus 4 sevenths? Hopefully we would have said 5 sevenths. Each term just happened to have an x with it. Okay? Alright. What if, just trying to think of another one. What if, okay, this is a pretty minor change to it, but what if it's 3x on 7 plus 4x on 7? Well, 3x and 4x, that's 7x on 7. But here, I'm jumping ahead a bit, but we're about to do, well, we've done some simplification. I can say, no, there's a 7 on the top and there's a 7 on the bottom. Hopefully you can see that I've got 1 7 here and 1 7 here. Fractions, even in algebraic form, follow the rules of fractions where I can look for common factors. So what have I got? I've got a 1x on 1, and a 1x is just an x, and an x on 1 is also just an x. 7 on 1 is normally written 7. We don't bother writing on 1. An x is just a number. Again, I wouldn't normally put in all that working. I can see that the 7s went, and I was just left with an x. Okay? I'll just make the point here, be careful of stuff like this. If you end up with something like a 5 on 5x, that's not x. Let's look at it carefully. I've got 1 5 there and 1 5 there, so I've got a 1 on the top and a 1x on the bottom. So sometimes it's easy to go, oh look, the numbers are gone, I've just got an x left. Yeah, I do just have an x left, but this x is on the bottom. Okay, just check where it is, it's all good. So more examples. This one here, I never remember to press that button, do I? 5m on 8 plus m on 2. Well, that's not a common denominator. Don't go adding tops and all that. Remember, we need a common denominator. But my tactic was to go to the biggest one and ask if it'll do the job. In this case, the answer is yes. I can easily change a 2 into an 8. So I'm going to leave the 5m on 8 alone, but I'm going to times the 2 by 4 to become an 8. Or better, times the top by 4 as well. And what's m times 4? It's 4m. Now I've got some like terms on the top that I can add, and the common denominator, which was essential, and 5m plus 4m is 9m. I could simplify that if there was common factors, but there aren't any, apart from 1, which doesn't help us. The answer is 9m on 8. Yep, simplified. Okay, right, the next one. 9 on x plus 2 on 3x. It's a bit of a leap, actually, because there's a concept here which, whereas it's not essential, I've written both ways, I think it's really nice to spot. What's the common denominator here? And I might bring up a number example, which is going to look odd, but what if I said 1 on 4 plus 1 on 3 times 4? Would you agree that 3 times 4 is 12, and that 12 would be a nice common denominator, because 3 times 4 contains a 4, so that will do the job. The point being, the main thought here might be, well, I don't know, let's just make a common denominator of 3x squared. Do I really need the squared? Would you agree that if you look at the big one and ask, is 3x a multiple of x? The answer is yes. It's going to be easy to convert this x into a 3x. I'm going to times the bottom by 3 and times the top by 3. So yes, you could just go through this method where you basically do the cross method. Algebra times algebra gives 3x squared on the bottom. 9 times 3x is 27x, 2x, yep. But as you've seen in fractions, the lowest common denominator is better. So what I want to do here is just leave it, the denominator is 3x, and it's become 27 plus 2 on top, which is 29. So my answer is 29 on 3x. In the other one, I had to get 29x on 3x squared, then remove an x. Didn't kill me the extra time, but we know that lowest common denominator is better. So if you spot that, I'm going to make up another example. Say we had 2 on a squared b plus 3 on ab cubed. Alright, I'm going a bit for the jugular. But I want to find a common denominator that has an a squared b in it and has an ab cubed in it. And I don't want to just go for, I could times it. What's a squared times a? Well, that's a cubed. What's b times b cubed? Well, that'll be a b to the 4. That denominator will work. But do I need that many a's? No. I need an a squared and I need an a. An a squared will do. I don't need an a cubed. I just need a number that contains an a squared and an a. An a squared does contain an a squared and an a. What's the biggest number of b's I need? I don't need b to the 4. I need a b cubed. This is my lowest common denominator. And let's check. I'll do it. I'm still going to do it in 2 separate fractions. Now I'm going to convert these both to a squared b cubes. What happened to this denominator? A squared b, how did it become a squared b cubed? It got times by a b squared, because the only thing different is b became b cubed. So if the bottom got times by b squared, the top had better get times by b squared. It's 2b squared. Now what happened to ab cubed to get to a squared b cubed? The only thing it got times by was an a. A went to a squared, the b cubed stayed. So the 3 only needs to get times by an a, so it becomes 3a. And now, so I've got a common denominator of a squared b cubed. And on the top, well, I know I can't add them, they're not like terms, so I've just got to write them. 2b squared plus 3a. That is simplified. I've turned 2 fractions into 1. I've done all I can. I can't simplify the top. And the fact that I use the lowest common denominator, well, I'm simplified. We're done. So that's about as hard as it would get. Okay? Let's check the next one. Simplify 3x on 4 minus 2x on 3. Well, there's no letters in the bottom. It's just good old 12. We're not finding a better denominator than 12. So I'm going to turn them both into 12s. The 4 got times by 3, so the 3x will get times by 3. 3 by 3 is a 9, and there's still an x there. 3 by 3x, I can combine the 3 by 3, it's still got an x. The 3 got times by 4 to get to 12, so 2x times 4 will become an 8x. 2 by 4 is an 8, and there's still an x. I've got like terms on the top. I know my denominator is 12, and 9x minus 8x is just an x. I could write 1x, but just an x. That's all I can do. Great, simplified. Now multiplying and dividing. They're the nicer ones. And I've written it out with crossing and that, but it's a lot better to watch it live than watch it already typed up. 5 on x times x on 10. Now, first rule of multiplication was, if you want, you can just multiply them out. You can just say, I'm just going to do 5 times x, and I'm going to do 10 times x, which is 10x. And then you might say, well, I've got an x on top and x on the bottom, they can cancel. And I've got 1 5 here and 2 5s here, so I've got myself a half. But I do think it's nicer to, I'm quite confident, to write the right question, but also do your simplification before you bother timesing. In this question it didn't get too bad anyway, but just to say in the question, only when it's multiplication, I've got an x there and x there, they can go. I've got 1 5 in 5, I've got 2 5s in 10, and I'm left with, now I could have put 1s here, there's 1x in that, there's 1x in that. I've got a habit of just going, oh look, the x's are gone. But 1 times 1 on the top and 1 times 2 on the bottom. Okay, so that's what happened here. That's pretty nice. The next one, I've got a 3b on 2 times a 4 on 5b. I can instantly spot there's a b on top and bottom. It's not an algebra question anymore. We're just back to basic fractions. But let's look for cancelling. 3 and a 5, I don't think so, but 4 and a 2, we've got 2's in them. 1 2 there and 2 2's there. We've got a 3 2's, a 6 on the top and a 1 by 5 on the bottom. And remember, there's nothing wrong with 6 on 5. I could have written it 1 and 1/5, but I really don't care. And especially, just say I changed the question and said, oh look, no, there was an x in there too, and there's an x in the answer. I definitely never change that to 1 and a 5th x. It's actually in algebraic fractions, it's more preferable to have the improper fraction. So if you're a bit wary at leaving improper fractions, I promise you it's a good thing. Even in the non-algebraic section, but definitely in the algebraic section. It's fully simplified, there's no common factors, it's beautiful. Alright, the next one goes to a division. AB on 2 divided by B on 5. Alright, I know that with divisions, I don't try and cancel anything, I only do that in multiplication. In every division question, I'm going to do the invert and multiply. Leave the first one alone, but invert and multiply in the second bit. Division becomes times, and the b on 5 becomes 5 on b. Now look for any simplifications. I can lose a b off the bottom and the top. Nothing else, so this is my final answer. 5a on 2, 5a on top, 2 on the bottom. And again, if you want to put the 1s, a times 1 times 5 is 5a, 2 times 1 is 2. Alright, the last one. 8a on 3b divided by 2a on 9b. Well, leave the first one alone. 8a on 3b times 9b on 2a. There's an a on the top and the bottom. There's a b on the bottom and the top. Great. A 2 and an 8. No, it's all coming up Millhouse. I've got a single 2 there, and I've got 4 2's there. 3 and 9, I've got a single 3 here and 3 9's here. That becomes 3 4's on a 1 1. 12 and 1, that's just number 12. There are 12 of them in that. I think that's us. Hey Joan, yeah, on to exercises. So, you see, yeah, some light terms there, a bit of multiplying, division, and then proper algebraic fractions. I wrote a fair few today, plus, minus, times and divides, and some substitutions. So, hope that was useful. That's our intro to algebra, and hopefully if you have had algebra allergies, I hope that this intro will say, okay, no, it's not that bad. I hope so anyway. Okay, see ya.